These guys have had problem sets already. All right, so let's go ahead and just do a quick recap of what we talked about last week. And so let's consider a couple different assets. Asset 1, given by negative 503, 140, 350, and 100. Asset 2, given by negative 689, 120, 550, 150. And asset 3, given by negative 374, 70, 300, and 75. So given a collection of assets, one of two possible scenarios can hold. Either A, you can construct an arbitrage portfolio out of them, or B, a certain linear equation holds, right? Or a system of linear equations, right? And so you basically killed two birds with one stone. By setting up the linear equation and solving, you're going to both determine whether or not it's an arbitrage, whether or not you can construct an arbitrage portfolio, and you'll also be able to find the associated y's in the case that you can't, right? So anytime you have a collection of assets, we're just going to toss them together into a matrix, and we're going to set up the matrix equation. And let me just make sure I get my notation consistent here. Yeah, y naught, y1, y2, y3 times this matrix, where we just squish them all together. Negative 503, 140, 350, 100. Negative 689, 120, 550, 150. Negative 374, 70, 300. So to set that equal to 0. And so we like to take the transpose so that we can do row reduction instead of column reduction. I don't think I've ever seen anyone do column reduction before. So I will not be the first. Take the transpose. Column 1 becomes row 1. So this times these y's equal to 0. That's the system we want to solve. And so this next step, I want to give you guys a big hint when you're working on not this homework here, the inequalities and arbitrage portfolios, but the next one, which I can't remember the name of it. A big hint in constructing your own systems in which you don't have arbitrage portfolios is you want to get a matrix like this, that after you row reduce it, if you can get ones, so basically 1, 0, 0, 0, 1, 0, 0, 0, 1, have a bunch of ones and zeros, and then have one column in which you have all negative values, then that's a really easy way to make sure that you're not going to have an arbitrage portfolio.
from the customer standpoint, all those negatives are those negative cash flows?
It gets a little bit complicated because remember that state, so state 0, that's when you, sorry, not state 0, time 0. I guess you'd be receiving $1, and then in time 1, you'd be paying 10/9 of $1. But then in this case here, remember that this is actually state 1, and this is state 3. So we don't really have, I guess you'd pay 0 in this case. And you'd either be obtaining $1 or paying 19/18 of $1. So yeah, it gets a little bit mixed up when you start row reducing because we've basically grouped year 0 and year 1 into the same matrix. And so, but now we can unpack this matrix into a linear system, and we get 1 times y0 minus 10/9 y3 equal to 0. And 1 y1 minus 19/18 y3 equal to 0. And y2 minus 8/9 y3 equal to 0. And this, of course, is equivalent to y0 equal to 10/9 y3, y1 equal to 19/18 y3, and y2 equal to 8/9 y3. So the next step that we're doing here is motivated by the definition of the arrow prices. Remember that the arrow price, pi of s, is given by ys over y0. So pi of s is equal to ys over y0. So what we want to do, we want to get to a state where we have the y's's all isolated, and we have y0. So let's by itself. So we can take, if we want to isolate y3, then from equation 1 there, we see y3 is equal to 9/10 y0. So we've got y3 by itself written in terms of y0. And from this, if y3 is 9/10, we can plug that into y2, right? y2 then becomes 8/9 times 9/10.
4/5.
Which, 4/5. Why not? And making that same substitution into the second equation tells us y1 is equal to, we have 19/18 y3. 19/18 y3, so what is that?
19/1.
Yeah, 19/20. 19/20. Why not? So this is all motivated by the definition of the arrow prices, which said if you can find ys as a function of y naughts, divide by y naught, then you get your pi of s's. So there we have our y's's. And so now I can set up our arrow prices. Pi of 1 says take y1 over y0. y1, we know was 4/5 y0. And so pi 1 is going to be 4/5. Pi 2 says take y2 over y0. Oh, sorry, that should be 90.
19 over 20.
19, yeah. Yeah, pi of 2 says y2, which that one's 4/5 over y1. And then pi of 3. 3 is 9/10 y0. So dividing by y0, just 9/10.
Can you explain to me again how you do that, the number?
Yeah, these, the pi's.
Uh-huh.
Yeah, so pi of s just says take ys divided by y0. So, for example, y2 is 4/5 y0. And so when we divide by y0, we'll get the 4/5. Just basically just using this one. Right? y2 divided by y2 divided by y0. Using the 4/5. All right, so those arrow prices tell us the price that we should pay for an asset that pays. So if we're looking at pi of 1, for example, it tells us the price we should pay today for an asset that pays $1 in state 1 next year. Pi of 2 says the price we should pay today for an asset that pays $1 in state 2 next year, and so on. And so the Arrow-Debreu securities are simply remember that the cash flow vector has a negative in the 0th entry, right? So we should pay, for asset 1, we should pay, meaning negative 19/20ths, and we'll get $1 and $0 in states 2 and 3.
Negative 4/5 to 0, 1, 0.
That's right. Yep. Negative 4/5, that's the price we should pay today to get an asset that pays $1 in state 2. And same thing here, negative 9/10. Sorry, yeah, negative 9/10 of $1 for an asset that pays $1 in state 3. And so someone remind me, what's the definition of a risk-free security? You guys can answer too.
Is where all the possible states are 0 or greater?
No, not quite. I can see how you're thinking about it. Gil, did you watch this video or something? No? So, a risk-free asset, remember, is one that returns the same value in every state of nature, right? So, in this case, all we're going to do, we're going to take a sum of these arrow securities, and what's going to happen? We'll get $1 in state 1, $1 in state 2, $1 in state 3. So the sum of the arrow securities is going to give us a risk-free asset. And adding these fractions together just gives us negative 53/20. And so remember, that's the definition of a risk-free asset. one that returns the same amount in each state of nature. Okay. All right. So remember that the risk-free rate says take the payout in state 1 divided by the payout in state 0 minus 1. So that was a formula that we talked about when Ben was here. We mentioned what's going on with the negatives. And the negative is part of the formula for the cash flow vector. So P naught is actually positive, and that negative comes from the formula, right? So P1, that's the price in state 1 for a risk-free asset. It's the same as for all the others, right? So we just need to pick out P1. P1 is 1, and P naught was 53 over 20, positive, right? Because the negative just comes from the cash flow vector itself. And computing that, I'm not even going to attempt to do these fractions. Negative 33 over 53. So that's the risk-free rate of return.
The numbers are made up. Is there a lot of situations where people like to pay more for a security than the security will let them pay out?
So, yeah, I mean, it's not typical, but there are definitely lots of situations like the safety deposit box is one, where you pay money to keep whatever item it is safe. So
I see. Yes, definitely.
Yeah.
Thank you for that example.
Yeah, and so it's definitely less common. You actually want an asset that's going to pay you money, but yeah, it's something that you will actually see in certain systems.
Thank you. I forgot the example. That makes sense.
Good, yeah, good questions. Any others?
So why the sum of Arrow securities? Why would you do them up?
Just because we want to cook up a risk-free asset.
Oh,
And so
okay.
yeah, it's sort of a freebie. Once you have the Arrow securities, you get the risk-free asset for free because you get to just add them all up and you automatically get the same return in each case. In this particular system, these Arrow securities and these Arrow prices are unique. But in a lot of systems, that's not the case. And actually, Charles, this is another interesting comment related to the question you had first of, why is it that we're paying money to own this asset, and how often is that going to come up? There's actually a lot of situations where the Arrow prices and the Arrow-Debreu securities, and therefore the risk-free rate, are not necessarily predetermined. You can have families of Arrow prices, Arrow-Debreu securities, and risk-free rates. And what happens is you have this equilibrium where you have people have endowments, people have budget constraints, people have preferences, and putting all that stuff together, you get a certain risk-free rate out of the entire collection that you could have in this particular setup, right? So this gives you a collection of all possible Arrow prices, Arrow-Debreu securities, and risk-free rates, and then you use equilibrium analysis to determine which one is actually taking place. So in a more typical example, it's not going to be unique. In this particular example, I chose it so that it would be guaranteed to be unique, but that's another thing that can happen is that under equilibrium, people may end up choosing the one that sort of matches best with their preferences. And so in that case, you see the risk-free rate is actually a lot higher than it is here. So that's another thing.
Thank you.
All right, good. So let's go ahead and take note of the structure that this risk-free rate has. You'll notice that in the risk-free asset, this set of Arrow prices added to give us that particular P naught. So that negative 53 over 20, that was equal to pi of 1, pi of 2, and pi of 3. And so what happens is, this equation that we're looking at here can be rewritten. As the risk-free rate is simply equal to P1 over the sum of the arrow prices, sorry, pi of S, minus 1.
Out of the same thing.
Yeah, because the P naught is simply the sum of the arrow prices, right? And I guess it should have, instead of a negative here, it should have a positive. And so what we can do is, let's go ahead and solve for the sum of the arrow prices. I'm going to skip the algebra here. But I'll at least say it out loud, right? Add 1 to both sides, multiply by the sum, and divide by 1 plus r. And we get the sum of the arrow prices is equal to 1 over 1 plus r. And I'm hoping that 1 over 1 plus r is giving you warm, fuzzy feelings right now. Because that's a discount factor, right?
Yeah, there was something.
Yeah. So in other words, the sum of the arrow prices are a discount factor that you can use for discounting future payments for a risk-neutral investor. And so really, a choice of arrow prices essentially determines this discount factor. And this would be used for risk-neutral investors. Remember, risk-neutral investor is someone who says, I don't care if I get the risk-free rate or the risk-free rate on average. As long as overall, if I play this game repeatedly, as long as I'm getting the average equal to the risk-free rate, I'm fine with that. This is the discount factor that they would use in valuing their assets. That's their hurdle rate. Yeah.
In the sigma pi of S equals 1 over 1 plus r, is P sub 1, does that become 1, or are we assuming it to be 1?
Which, this guy here?
Yeah.
Oh, I see what you mean.
What happens to P sub 1?
Yeah, I'm guessing I dropped that by mistake. Let me see. Yeah, in my notes, I dropped that by mistake, so it should be,
P sub 1.
yeah, I think implicitly I'm using the fact that P sub 1 is equal to 1. Right.
Okay.
Yeah. Yeah, because this is the risk-free asset, and you can always do that. Once you have the risk-free asset, you may have something different from 1 here, but you can always just apply that, and then you get 1 here. Yeah. So anyway, yeah. So if you had a P1 here, then you'd have other P1s floating around, and it would end up dividing after manipulating it. Yeah, I'm glad you caught that. So it's more than that, though. I mean, that's already pretty cool, right? Because on some level, what this says is that a choice of Arrow-Debreu securities, a choice of Arrow-Debreu prices, and therefore Arrow-Debreu securities, essentially determines the discount factor. So these things are kind of equivalent in some sense, discounting and arrow prices. There's sort of a dictionary between the two, right? But it gets even more interesting than that when you make a slight rearrangement of that previous equation. Which says we've got this sum of the arrow prices giving us a discount factor 1 plus r. And we can rearrange this as 1 is equal to 1 plus r times the sum of the arrow securities, arrow prices rather. And so this may not look like much, but let's go ahead and dissect it a little bit. And we'll notice after we sort of dissect it that it has a very, very interesting interpretation, right? Let's go ahead and recall the pi of s's were given by ys over y naught. And Steenka's theorem guaranteed that these things were going to be positive, right? We're only taking the positive case of Steenka's theorem where you get these positive y's. They give us positive ratios. So these things are positive. Okay. This 1 plus r is always positive. And so what you'll notice is that we have a sum of values that are all positive that add to 1. And what that tells us is that this actually represents a probability density, right? Because we basically have the following outcomes. We have state of nature, and we have state of nature 1, state of nature 2, state of nature 3, all the way up to state of nature, we'll say k. And we have these terms here. 1 plus r times 5s. And so we've got 1 plus r times pi of 1, 1 plus r times pi of 2. And the fact that these things add to 1 basically tells us that what we're looking at here is a probability distribution. All possible outcomes and their associated probabilities. Right? Some questions so far? And so, anytime you have a probability distribution, you can use that to compute expected values. Sorry. So I was going to recall that the value that we pay today in state of nature 0 for the ith asset is equal to the sum of the error prices times the outcome times the price in state of nature S for asset I. We talked about this last class. And so let's take the expected value of both sides. price that we pay today for asset I is equal to the expected value of this sum. And this is equal to 1 plus r times the sum pi s. P1 I of s. But this thing is equal to simply P naught of I. Man, I'm sorry, something's off here. It's a quick fix session to reinterpret something. Oh yeah, of course, yeah. So, sorry, it should say P1 here. The expected value of all the P1s is equal to the expected value of this sum. That sum boils down to the value of the asset to I. And so now we can solve for P naught I. So P naught I we get the price that we pay today of the ith asset, just dividing through by 1 plus r, is equal to the expected value over this variable P1I over 1 plus r. And this is about as close to a punchline as you're going to have for this course. This is like everything that we've done from day one, all put together, right? And so basically, this is what this equation tells us. For a risk-neutral investor, meaning someone who is okay getting an average rate of return equal to the risk-free rate, the price of asset I today is a probability-weighted sum over the possible future states. Where the probability is given by the terms 1 plus r pi of s for each state of nature. One last little thing that we do is this sum is discounted back to the present. at the risk-free rate. So it's quite a punchline. There's a lot going on. But you've got this random variable. P1i is a random variable because it depends on the state of nature. Sometimes it'll be state 1, state 2, state 3, state 4, so on. So you're going to weight all those different prices according to these probabilities, right? So you've got this probability distribution obtained using the risk-free rate and the arrow prices. So that gives you a probability distribution. If you weight those prices according to that probability distribution and take the average using those weights, that gives you a sum of all the future values weighted according to this probability. So that's the sum in the future, or sorry, that's the value of that asset in the future. It's the weighted average of all those possible outcomes, right? So if you have the value in the future, we know how to move that back in time. 1 plus r takes the value, probability weighted value, and discounts it back to the present time. And so it's, there's a lot going on here, but at the same time, I hope you guys agree, it's rather pretty. And we're going to talk a little bit more about this in a couple minutes, but any questions before we go on?
So, the sum of all these prices equals to 1, or the sum of the, not clear with this, so, those are different states, right?
Yeah, you've got your different states here. And you've got these arrow prices.
Okay, so the sum of all those arrow prices is 1.
Sort of, yeah. The sum of the arrow prices times this growth factor
Oh.
equals 1. Yeah. And so that gives you a probability distribution. Yeah. So that probability distribution can be used to take the weighted average of all the prices in the future. So that's the expected value. Expected value gives you the weighted average, weighted according to these probabilities. So that gives you the price of the asset 1 in the future. Okay, so this is the price of asset 1 in the future. If you want the price of the present value, discount that. I do have some arithmetic I can show you guys. It's nothing fancy. It's nothing interesting. But I at least went through. Sometimes it helps just to have some numbers floating around. I went through and did it for this set of assets that we started with. And so we've got, okay, here's our state of nature, 1, 2, and 3. And we know that in the states of nature, the probability associated with that is going to be this 1 plus r. In this case, r was negative. So 1 plus r times the arrow price for that security. So these are now probabilities, right? They are values between 0 and 1, and they add to 1. So these probabilities, you're going to multiply. So here we're looking at asset 1. Okay, so asset 1 in state of nature 1, the expected value, meaning the average of all those prices, there's 140, 350, and 100. Those are all the future prices. Weight them according to this set of probabilities. So that probability, that probability. So you're weighting them according to the probabilities, and you get 1060 over 53. And so what is the price of asset one at time 0? Well, it's the price of asset one in time 1, which is the weighted average that we just got computed, discounted back to the present. You go through and do that calculation, you get 503.
And in this asset one, you can get 140, 350, or 100, depending on the two states.
That's right. And so what is that 503? Well, that's what we paid. So basically, it's a way of saying, for a risk-neutral investor, what is the risk-free rate that's sort of implied by these assets? If you're going to pay if you're going to pay 503 today for this, there's a certain risk-free rate and a certain set of probabilities associated with these future payments for which that investor is willing to pay 503 in such a way that it balances out to give an overall risk-free rate on average over time.
Yeah, I got it, but the question is, can you find the amount, can you find the probability for each state?
Well, so here's the thing, right? Here's the thing. This is what's really frustrating about risk neutrality. Risk neutrality doesn't necessarily have anything to do with the real world. Risk neutrality is a way of encoding that no arbitrage principle, right? Because basically, what we've done here is we've got this collection of assets, and what did we do with them? We created our own risk-free asset. So one of two things could happen. Either A, that's the only risk-free asset that we have, or B, there's two risk-free assets. But if that's the case, then you have an arbitrage opportunity, right? So that risk-free rate is, and risk neutrality, it's not necessarily what the probabilities actually are. It's the probabilities you need to ensure that no arbitrage exists. And so, relative to that risk-free rate, right? And so, basically, in models that use risk-neutral pricing, you're using that assumption of no arbitrage to, kind of like what we talked about a couple weeks ago, generate, if you can generate a risk-free portfolio, then what you can do is you can use that principle of no arbitrage and say, well, I know what the risk-free rate is, and here's a portfolio that's supposedly risk-free. Based on that, I can pair up this portfolio with this risk-free rate, and I can then deconstruct the prices that I have that went into that portfolio. And so it's a way of using that no arbitrage principle that you have this sort of anchor called the risk-free rate. Using that no arbitrage principle and that anchor, you get to deconstruct what are the prices that should be going into this portfolio, right? And so, yes, it's a very, very subtle concept. I didn't bring this book along intentionally. I actually had just been working in it, and I shoved these papers into it and just brought the whole thing with me. But it's interesting, this actually has some really interesting comments on risk neutrality. So, a rather different view of option valuation from that presented above is the risk-neutral approach. This stems from the observation that the growth rate mu does not appear in the Black-Scholes equation. Therefore, although the value of an option depends on the standard deviation of the asset price, it does not depend on its growth rate. Let me get to the good stuff here. So they go through this, and mu ends up dropping out. You end up getting an R, the risk-free rate. So let's pick up here. It says the idea of replacing expected return by the risk-free rate is very elegant. It does, however, have some major drawbacks. First, it requires us to know the probability density function of the future asset values under the risk-neutral assumption. So that's these on the bond. And what we'll do is, if they can't actually make that payment, then they'll just pay whatever they can. P1x of S is whenever they can't actually make that payment, they'll just pay whatever they can.
And so would these be based off of particular criteria, like a balance sheet on their asset, or part of their assets balance sheet?
Yeah, exactly. Something where they've already paid their workers and they only have, you know, $1 million left and the interest they have to pay is, you know, $3 million. They'd at least pay $1 million after subtracting away their other expenses. So
Is this a common occurrence?
I think that oftentimes this would be considered a default. If they don't actually pay in full, it's some version of a default. And so-
Oh, okay.
Yeah, so it's a pretty big deal when this happens. So to summarize then, we've got these two different outcomes. The price at time one of this bond in state of nature S is equal to 1 plus the interest rate times the initial price if they can pay it. And simply some other amount, whatever they can pay otherwise. And so we're going to let S plus be the set of all instances where they actually make enough money to pay the entire amount due. And we'll let S minus be the set of all outcomes, all states of nature in which they didn't make enough money to pay everything that was due. And so, what price should we pay today, right? That's sort of what this whole thing has all been about, right? What price should we pay today to own that bond? Well, the sum over all the states, it would equal to the sum over all the states where it can actually make the payment, where this is the amount that they pay in those states, right? It's a probability weighted sum. And then the case where they don't make the payments is where they just pay whatever they have. And that's also probability weighted as well. So the probability weighted of these x's, P1x, where they just pay, you know, some amount, whatever they can find in the cash accounts. And what we notice is that these things are assumed to be smaller than the amount that they would have paid otherwise, right? So we notice that this is strictly less than the sum over all the cases where they can make their payments. Plus, so the probability weighted sum, plus the probability that they made their payments in the S minuses, right? These things are larger than these things, so we can set up this inequality here.
So, one more time. Not getting the inequality, so, second part of
So these P1Xs, this is where they pay whatever they can muster. And, oh, I'm sorry, there should be a 1 plus I times P1B. The other case is where we say, we know these are going to be smaller than what they would pay otherwise. So if we replace these with what they would pay otherwise, then this is certainly going to be larger than this, and therefore this sum is definitely going to be larger than that sum. And what you'll notice is that this is simply the sum 1 plus I P naught B times the sum of the pi s's. But what was the sum of the pi s's?
One. This is almost exactly how they figure out insurance rates, just for the position. If you're the insurance company, how much should you charge?
And so, okay.
Yeah.
Yeah,
It's the exact same situation that they crunch.
Interesting. Yeah, it sounds to be pretty much identical to that. Sorry, instead of 1 it should be 1 plus,
R.
it should be 1 over 1 plus r, sorry. Right, the sum of the pi s's was 1 over 1 plus r.
yes.
Yeah. Okay. And so we get 1 plus I over 1 plus r times P naught B must be greater than P naught B. And what that says then is 1 plus I over 1 plus r must be greater than 1. And so the interest that you would charge for that bond is greater than the risk-free rate. And that sounds completely natural, right? Where you say, okay, clearly, if they're going to be missing some payments, you don't want to lose money that you could be getting, right? If you just invested at the risk-free rate, everything would be fine. And so clearly, you don't want to be missing out on anything that you could be getting, so you're going to charge a little bit of extra on that bond to compensate for the probability of reduced payment, right? And it sounds like you're looking at some sort of risk-averse behavior, where you're saying, oh, no way, I'm not going to give you the risk-free rate, I'm going to bump up the interest rate, right? And even though that sounds like risk-averse behavior, it turns out it's actually not risk aversion. This is what we were talking about with risk neutrality. This argument has nothing to do with risk aversion. What it really has to do with is simply making sure that you get the risk-free rate on average, right? Because if you're going to miss certain payments, then if you had set the risk-free rate here instead of this interest rate that you actually gave them, if you're going to miss some payments, you're not going to get the risk-free rate overall. It's going to be below the risk-free rate. And nobody wants to get below the risk-free rate. So you're going to bump up the interest rate a little bit, and that's going to compensate for the lower payments that you're going to get in some states in the future. But does that mean that you're risk-averse? No, actually. All that you're doing is you're literally just making sure that you get, on average, the risk-free rate. And so this all goes back to that whole idea of risk neutrality. But yeah, this has nothing to do with risk aversion. All that this I does is it says, I could charge you the risk-free rate, but since you're going to miss payments, I'm going to bump up the interest rate I do charge, so that on average, I'll get the risk-free rate. And so that's not risk aversion. That's really just...
Because that state can still occur.
Yeah, exactly. So you miss out on that money. So it's not actually risk aversion, though. It's literally just arithmetic, where you say, I want the risk-free rate. So once you start getting into utility, that's when risk aversion starts coming. And if you have utility curves that are risk averse, then these people say, you know, I know you're gonna miss payments, and I'm okay with that. I'll just pump up the interest rates so they're on average. the risk free. So. All right, well, thank you so much, gentlemen. Hope you guys learned a lot. So next week, I mentioned that it'd be fun to sit down and do some problems. So sorry about this last problem here. I reviewed it this weekend, but I didn't write up my own notes, so it wasn't real fresh. Fumbled a little bit there, but hope you guys could follow it okay. Any questions before we